So I think the title of my talk was worries about probability in Everettian pictures of quantum mechanics, or something like that. Actually, it's going to be narrower than that. I'll talk about that in a minute. Anyway, and it's going to be a lot. A lot of what's going on here is going to be repeating things that Sean said in the first half of his talk, but slower and more pedantically and in a more somber tone of voice. So there's this long-standing puzzle about how to make sense of the standard quantum mechanical talk about probabilities in the context of the Everett interpretation. And one way of presenting this puzzle is to point out that Everettian pictures of the world seem not to have any room in them for ignorance about the future. The thought is that the Everettian picture of the world, whatever precisely that picture is going to turn out to be, is going to be completely deterministic, and moreover, it's going to impose none of the sorts of ignorance of the initial conditions that allow us to make sense of probabilistic talk in deterministic theories like classical statistical mechanics or Bohmian mechanics, or something like that. Good. So that's one way of setting up the traditional problem. And let me invite you to consider in this connection, much in the way that Sean did, the following kind of scenario that we'll be returning to again and again. Captain Kirk is about to step into the transporter on the Enterprise to beam down to the planet below. He happens to know that the transporter is malfunctioning at the moment. To wit, the transporter is going to make two Kirks on the surface of the planet out of the one Kirk that steps in on the ship, each of them dressed in a different colored outfit, one blue, one green. Both the Kirks initially arrive on the planet with their eyes closed, and more generally, with no indication at all of which particular one of the two Kirks on the planet they are. But each of them knows that they've arrived on the planet, and each one says to himself correctly, there is now some perfectly determinate fact of the matter about which particular one of those two Kirks I am. And each of them wonders which particular one they might be, and then they open their eyes and they look at their outfits and they find out. So consider this moment after they've arrived on the planet, but before they've opened their eyes. This is what Sean was referring to as the interval of ignorance, or something like that, when each of the Kirks is wondering which particular one of the Kirks he is. Lots of people, a whole academic industry of people, seem to think it makes sense for these Kirks to talk to themselves about the probability that when I open my eyes, I'll find that I'm this particular Kirk or that particular Kirk, or the probability that when I open my eyes, I'll see that I'm wearing a blue outfit or a green outfit. And this kind of talk would seem to amount to a way out of the puzzle that I mentioned above. This would seem to offer a way of talking intelligibly and reasonably about, quote, the probability that I'm about to have this experience and the probability that I'm about to have that experience, even in circumstances where I already know absolutely everything about the future physical condition of the world. The idea is that even in circumstances in which I have no ignorance whatsoever about the future objective physical condition of the world, I still might be ignorant, just as these various Kirks are ignorant when they're standing on the surface of the planet with their eyes closed, about where I'm located in that world. People call these sorts of probabilities self-locating probabilities, and there are whole bunches of aspiring Everettians, Sean, for example, and Lev Weidman, and other people, who've suggested that these may be precisely the sorts of probabilities that we run into in quantum mechanics. And basically, all I want to do this afternoon, all I want to try to do this afternoon, is to say why I find this kind of talk confusing. And a couple of things I should acknowledge. First thing I should acknowledge is that I owe everybody an apology because the title would have led you to expect a more comprehensive discussion of the various obstacles to making sense of probabilities in the context of Everett. And I had intended to offer something like that. And it wasn't until I got down to the detailed business of actually trying to imagine how to squeeze all that into the space of an hour, that it became clear that it was completely out of the question. So I thought the more useful thing to do would be to focus on the particular approach to these questions that I had heard Sean defending in the past and assumed correctly that he would be talking about today. Also, let me say that I'm just expressing confusions here, but I'm very thankful to have been able to talk to Barry Lower and Tamar Lando, both of whom helped me understand what I was confused about much better. Good. Anyway, there are different levels of confusion one might have about this Everettian strategy. There are a couple of small points that have specifically to do with quantum mechanics, and there are larger and deeper points that have to do with the whole business of assigning self-locating probabilities in general. Let me start, but I'll go through them quickly, with the ones that specifically have to do with the quantum mechanical case. So imagine that the adventures of Kirk and the transporter that we were just talking about correspond to an actual quantum mechanical Everettian splitting. Imagine that is that a quantum mechanical measurement, say a measurement of the X spin of an electron that's initially in an eigenstate of Z spin, whose result is encoded in the color of Kirk's outfit. Kirk's outfit is like the pointer on the measuring device, and the color of his outfit is like the position of the pointer, and Kirk himself is the sentient observer, and he becomes aware of the outcome of the measurement when he opens his eyes. And the thought is that the quantum mechanical probability that Kirk will see this or that particular outcome of this measurement is precisely the self-locating probability that I, Kirk, or I among the Kirks, or whatever it is I call myself, I'm going to find on opening my eyes that my outfit is this particular color or that particular color. Good. And a bunch of people have raised worries that Sean alluded to about, even if one can talk intelligibly about these self-locating probabilities, how they're going to apply in the Everettian case. So worries have been raised to the effect that this moment of uncertainty, this moment at which the Kirks are already standing on the planet in their differently colored outfits, waiting to open their eyes and wondering which one they are, this moment, that is, at which it finally makes sense to talk about probabilities, comes too late in the process. We're used to saying to ourselves, before we even undertake a quantum mechanical measurement, before we even step in, as it were, to the transporter, that we're uncertain about how the measurement is going to come out, and that the probability of the measurements coming out this way or that way is such and such. But it isn't clear how these ideas of self-locating probabilities are going to allow us to make any sense of talk like that. Remember that there's nothing whatever for Kirk to be uncertain about. Remember that there is nothing about the future condition of the world or of himself or of his descendants of which Kirk is ignorant. And that there's consequently nothing for any probabilities to be the probabilities of before he's actually stepped into the transformer and knows that he's standing with his eyes closed in his new outfit on the surface of the planet. the kind of thing that people have said in response to a worry like this is something like this. They say, look, the Kirk, before he steps into the transporter, knows for certain already that both of his descendants are going to be ignorant of something about the world. They're going to be ignorant of which one they are. Okay. And then the reasoning goes something like this. Well, look, this isn't because this Kirk forgot anything in the process of stepping into the transformer. Nothing gets, all the things that were in his memory before he steps into the transformer are still there in his memory once he appears on the planet with his eyes closed. Okay, so the thought is something like, if I know for sure that my descendants are going to be ignorant of something when they're on the planet, and if nothing has been forgotten between my stepping into the transporter and my appearing on the planet, then it must somehow be proper to attribute that ignorance to myself as well before I step into the transporter. That seems to me a bad argument. It's not that they forgot anything. It's that by the time they get to the planet, there are new centers of subjectivity. There are more centers of subjectivity in the world than there were before he stepped into the transporter, wondering where they are, okay? So there are questions that couldn't have been posed before. He's not ignorant of something because there's something he forgot in the process of stepping into the transporter. He's ignorant of something because there's now a new question that can be posed about a new centered world that didn't exist before. Okay, good. Anyway, I don't want to spend too long on that. I don't think that's a strong response. There are other worries associated with this. There are worries about whether this talk about ignorance and this business of assigning probabilities is going to make any sense in cases where Kirk, say, doesn't go to the trouble of keeping his eyes closed after he senses that he's arrived on the surface of the planet, and in cases where the interval between the completion of the measurement and the observers becoming aware of the outcome of the measurement turns out to be orders of magnitude shorter than the timescales associated with, say, the formation of even crudely rational human degrees of belief. Sean was emphasizing that there's always going to be a gap, say, between the time your eyes respond to stimulus from the outside and your brain forms a belief about what's being reported to it by your eyes. But I guess I'm just not sure if that interval is much shorter than typical intervals associated with cognition, what kind of sense it makes to speak of Kirk in that interval being ignorant. You know, suppose we did very careful strobe photography of such a person, and the careful strobe research revealed that for a very, very short fraction of a second after landing on a planet, but before opening his eyes, all the Kirks actually turn into billiard balls. And then they turn back into Kirks once they get, you know, once their eyes are opened a tiny millisecond later. Are we going to want to say that the billiard balls are ignorant there? There's some sense in which the Kirk during that interval is no more of a cognitive being than the billiard ball was. Okay, another level of confusions on my part that I don't want to go into too much. Third level. Is there anything, Sean talked about your eyes communicating with your brain, but look, is there anything that in principle that stands in the way of these two events, that is the completion of what Sean calls the pre-measurement and the observers becoming aware of the outcome of the measurement? Is there anything in principle that stands in the way of those two being perfectly simultaneous with one another and even perfectly identical with one another? That is there anything in principle that stands in the way of a setup in which the first macroscopic degree of freedom that becomes correlated with the measured property is also a macroscopic degree of freedom which determines the observer's occurrent conscious perception of how the measurement comes out? And finally, on the quantum mechanical level, you ask all these questions and then you start saying to yourself, gee, the necessity of even discussing these questions about exactly when it is that measurements come to an end and about exactly when it is that an observer becomes conscious of this or that. These are connections which should make us, these are the kinds of questions which should make us queasy in discussions of the foundations of physics. These are the kinds of questions that should remind us of bad old days when people were talking about Wagnerian sorts of models of measurement where consciousness was playing some crucial role. This is the kind of conversation that ought to give us pause. Anyway, I just want to mention those worries because I think they end up being the more superficial set of worries in this conversation. I think they're serious worries. I'm not aware of any of them having been given what has struck me as a fully satisfactory answer, but I want to go on with the rest of the talk as if none of those are really serious worries, because I want to bring to the center what strikes me as a deeper question about the meaning of self-locating probability, both as it applies to Everett and more generally. So the bigger question, the more fundamental question, like I said, has to do with whether talk about self-locating probabilities in general makes any sense. And one way of raising that question that I think will be useful here, and I think this is related to what Mayor Himo was talking about in the question period, one way of raising that question is to compare these self-locating probabilities with the kinds of probabilities that we run into in classical statistical mechanics. So let me talk for a few minutes about classical statistical mechanics. This will have to be quick, but I take it much of it will be familiar to most of you. Let me start by stating what it'll be convenient to call, for this conversation, the fundamental hypothesis of statistical mechanics. Here's what it is. Consider a true thermodynamical law, any true thermodynamical law, to the effect that macro condition A evolves under such and such external circumstances and over such and such a temporal interval into macro condition B. Whenever such a law holds, the overwhelming majority of the volume of the region of phase space associated with macro condition A, according to the standard Lebesgue measure, or what's sometimes referred to in the physical literature as the Louisville measure, on the phase space of the system in question, that is, the overwhelming majority of that volume is taken up by micro conditions which are sitting on deterministic Newtonian trajectories which pass under the allotted circumstances at the end of the allotted interval through the region of the phase space associated with macro condition B. That's a long sentence, but its content, I take it, is old news to everybody. Here, the whole of the science of statistical mechanics can be described as a sustained attempt at making it plausible that precisely this hypothesis is true. Of course, proofs are out of the question, except in the simplest and most restricted sorts of situations. But let's put that aside for the purposes of this particular conversation and simply assume that the hypothesis is indeed a theorem of, say, Newtonian mechanics. Okay, good. And now consider a postulate call it the statistical postulate, that runs like this. Take an arbitrary thermodynamic system called S and some arbitrary possible macro condition of S called A, and let capital R sub A be the region of the phase space of S that's associated with the macro state A, and let little r sub A be any subregion of big R sub A. Then the probability that the micro condition of S lies in little r sub A, given that S is in the macro condition A, is equal to the standard Lebesgue volume of capital R sub A divided by the standard Lebesgue volume of little r sub A. That's also a long sentence. I should have made slides, I'm sorry. But I take it this is a postulate with which everybody is familiar. True. Okay. If the statistical postulate is true, and if the fundamental hypothesis of statistical mechanics is true, then the two of them together will straightforwardly entail, the two of them together will straightforwardly explain the truth of the modern probabilistic versions of the laws of thermodynamics. There's, of course, a famous trouble with this explanation, which is that it works just as well going backwards. But put that aside for the moment. That has nothing directly to do with our business here, and it'll be a very straightforward matter if people want to talk about how to patch that up during the discussion period. The way to patch it up is to add something like a past hypothesis. This also everybody's familiar with. That's not what we want to talk about here. What I want to focus on here, what'll be relevant to the discussion about self-location, is the nature of the statistical postulate. There's a long tradition of suggestions to the effect that the laws of thermodynamics in their probabilistic form can somehow be obtained from or described in or dug out of the underlying microscopic laws of motion alone. These suggestions have to do, that is, with one way or another of imagining that the other premise of the argument, the statistical postulate, if one can only see it aright or say it aright, amounts to almost nothing. That it amounts, for example, to an a priori principle about how to reason, or an a priori principle about where the business of explaining properly comes to an end, or something like that, something other than a substantive claim over and above the dynamical laws themselves about the actual empirical nature of the world. Here's a famous example, a paradigmatic example, the principle of indifference. There's a thought, one that goes back at least as far as Laplace, that runs like this. Suppose that you know that a certain physical system is in one or another of a certain collection of n different possible physical states. And suppose that you know absolutely nothing more about the state of the system than that. Then there is an a priori principle of reason, a so-called principle of indifference, to the effect that you ought to proceed as if the probability that the system is in any particular one of those states is 1 over n. That is, you ought to assign equal probability to each of them. You ought to proceed as if you assign equal probability to each of them. And the application of a thought like this, the statistical mechanics, is presumably going to run as follows. If all I know about a certain system is that it's in a certain particular macro condition, then I know that it's in one or the other of the micro conditions with which that macro condition is compatible, and I know absolutely nothing more about the micro condition of the system than that. And if we pretend for a moment that all we ever do know about the conditions of thermodynamic systems are their macro conditions, that's false, but don't worry about it. And if we pretend for the moment that the number of distinct micro conditions in any given region of the phase space is proportional to the standard Lebesgue measure of that region, and that's nonsense. But forget about that too for the moment. Then it'll follow from the principle of indifference that I ought to proceed as if the statistical postulate is true. And the trouble with this even if we agree to overlook the falsehood and the nonsense, is that it isn't clear exactly what this admonition about how I ought to proceed is supposed to amount to. Two interpretations of this admonition come to mind. First interpretation: you ought to proceed as if the probability that the system is in any particular one of those states is 1 over n just means the probability that the system is in any particular one of those states is 1 over n. But this is preposterous. This is to read the principle of indifference as asserting that there is some a priori connection between what I happen to know and the frequencies with which certain particular kinds of physical systems are in certain particular kinds of physical states out there in the world, okay? And this, if you put it in these terms, is just madness. What kind of a priori connection could there be? What does the world care what I happen to know and what I happen not to know? Good. So I take it nobody is going to be willing to defend the principle in a form like that. Second interpretation: you ought to proceed as if the probability that the system is in any particular one of those states is 1 over n means your credence. Here's a word that Sean used. Your credence that the system is in any particular one of those states ought to be 1 over n. Good. And here, I guess, there are two logical possibilities to consider. Either the claim that your credence that the system is in any particular one of those states ought to be 1 over n somehow entails the claim that the probability that the system is in any particular one of those states is 1 over n, or it doesn't entail that claim. If the claim about your credence does not entail the claim about the probability, then the second interpretation of the principle of equivalence gets us nowhere, okay? Because what we want here, remember, is a deduction of the statistical postulate, okay? What we want is a deduction of a claim about the frequencies with which certain systems are in certain states. If we don't have something like that, we don't get an explanation of the truth of thermodynamics, okay? So if the credence claim doesn't entail the probability claim, then this version of the principle of indifference gets us nowhere. If the credence claim does entail the probability claim, then we're back to the first version, which is preposterous. Okay. So there would seem to be no sensible version of a principle of indifference that can get us from the microscopic laws of motion to the laws of thermodynamics. And it should be clear that there are no sensible a priori principles of reasoning, whatever, that are going to be able to get us from the microscopic laws of motion to the laws of thermodynamics. And all of this, I think, is as trivial as can be. And it seems like all of it ought to have been obvious to everybody from the outset. But the ineluctable historical fact of the matter is that it seems not to have been obvious to everybody from the outset, and appeals to something along the lines of a principle of indifference have played a central role in standard statistical mechanical accounts of the laws of thermodynamics ever since the pioneering days of Boltzmann and Gibbs. And principles like that continue to loom large in the imaginations of theoretical physicists, even to this day, and even in, say, Sean's account of the chances that we encounter in quantum mechanics. It's interesting to speculate about why this had such a hold on people. I mean, I think all of it can be traced back to the peculiar intensity of the longing to somehow get thermodynamics out of the microscopic dynamical equations all by themselves. And there's a lot to say, I think, about why that longing should have been as powerful as it was. Let me not try to go into that at all here. Anyway, there isn't an a priori route from the microscopic equations of motion to say something to something like the laws of thermodynamics. But that's the bad news. The good news, what you might call the miracle of statistical mechanics, what you might call the saving grace of statistical mechanics, is that all of the misunderstandings I've just alluded to end up doing no actual scientific damage. Because the statistical postulate, notwithstanding all the mishugas that I've just been through about where it comes from and how we know it and what kind of a claim it is, the statistical postulate turns out, in the end, to be true. There turns out to be nothing a priori about the statistical postulate, but that's fine, because there doesn't need to be. The statistical postulate is a claim about the objective physical chances of certain particles having certain positions and certain velocities. It's the kind of claim, that is transparently susceptible of confirmation and disconfirmation by experiment. It's an empirical claim. Thermodynamics turns out not to be derivable from the microscopic dynamical laws alone, but that's fine, because it doesn't need to be. The additional premise that we need in order to derive thermodynamics from the microscopic dynamical laws, the statistical postulate, turns out to be another perfectly kosher and empirically testable fundamental law of nature. And it turns out that we have good empirical reasons for believing that additional empirical premise is correct. Good. And now I want to turn back, with all this under our belts, to the Kirk case. The two Kirks are standing there on the planet with their eyes closed, wondering which one they are. And various hypotheses are entertained about the probability that when circumstances like this obtain, I am this Kirk or that one. And suppose that as in the statistical mechanical case, an a priori argument is presented, a principle of indifference argument is presented, to the effect that the correct probability distribution is 50-50. Once again, this argument is absurd. And it's absurd for exactly the same reasons as its statistical mechanical cousin was absurd. It's crazy to imagine that there is some a priori connection between what I happen to know and the frequencies with which certain particular kinds of physical systems are in certain particular kinds of physical states. And it is exactly as crazy as that to imagine that there's some a priori connection between what I happen to know and the frequency with which my outfit turns out to be blue. And once the absurdity of this argument is appreciated, the obvious thing to do, the thing we did at the analogous juncture in the statistical mechanical case, is to look into the possibility of determining the values of these probabilities by empirical means. And it's going to turn out that the values of these latter sorts of probabilities are not susceptible of being determined by empirical means. And this, it seems to me, is the crucial point, and this is the crucial difference between the present case and the case of classical statistical mechanics. Consider, just to have something concrete to work with, the following three self-locating probabilistic hypotheses. One, when circumstances like these obtain, the probability that I'm the blue Kirk is, say, 0.9. And the probability that I'm the green Kirk is 0.1. Two, when circumstances like these obtain, the probability that I'm the green Kirk is 0.9, and the probability that I'm the blue Kirk is 0.1. Three, when circumstances like these obtain, the probabilities are 50-50. And the critical thing to note is that the probabilities involved here, unlike the ones we were dealing with in the context of statistical mechanics, do not pertain to any aspect of the physical configuration of the world. And it follows that the various different probabilistic hypotheses that we're concerned with here cannot disagree with one another about any aspect of the physical configuration of the world. And it follows that the physical configuration of the world is going to be completely insensitive to the values of these probabilities. And it follows that these probabilities cannot be measured. It follows, that is, that there can be no physical procedure by means of which the inscription 1 can be made to appear on a piece of paper in the event that hypothesis 1 is true, and the inscription 2 can be made to appear on a piece of paper in the event that hypothesis 2 is true, and the inscription 3 can be made to appear on a piece of paper in the event that hypothesis 3 is true. And so the question of which one of these three hypotheses is true, supposing that one of them is not the sort of question that can be settled by means of objective empirical investigation. And the same sorts of considerations are clearly going to apply to hypotheses about self-locating probabilities in general. And that, it seems to me, is that. The question cannot be settled a priori, and I think this is what Mayer was saying in his question. The question can't be settled a priori, and the question can't be settled empirically, and so the question is not susceptible of being settled at all, and so the business of assigning probabilities to self-locating propositions and the business of explaining our experience of the world in terms of the values of the probabilities of self-locating propositions is nonsense. Maybe it's worth pausing here and emphasizing, because Sean was emphasizing again that again and again that the probabilities we're talking about here are merely empirical. These probabilities in quantum mechanics have a physical job to do. Okay, they're supposed to explain our experience. They're supposed to explain why the frequency with which we have certain experiences is larger or smaller than the frequency with which we have other experiences. So they have to be worldly enough to do something like that if they're going to do the job that we want them to do. Okay, anyway, so the question isn't susceptible of being settled at all, because it's not susceptible of being settled a priori, and it's not susceptible of being settled empirically. So the claim is that all this talk is nonsense. But look, maybe it needs to be acknowledged that this last bit goes by a little fast. Let me check the time. Yeah, maybe it needs to be acknowledged that this last bit goes by a little fast, and that it feels a little bit anticlimactic, and maybe it'll be worth taking a few minutes to get a more exact and more detailed and more concrete sense of what it is that actually goes wrong when we press this question as hard as we can and as far as we can and from as many different angles as we can think of. So let's try a few. Let's try this. Suppose that we undertake a series of obvious experiments, the aim of which is to measure the probability that I'm this Kirk or that one, as follows. Kirk steps into the transporter and beams down. There are two of him on the planet. Each of them wonders, which one am I? And they each open their eyes and find out and record the result. And then each one of them goes back up to the ship and steps into the transporter again. And each one of those two Kirks generates two new Kirks on the planet, and each of those opens their eyes and records the result. And the process can be repeated as many times as we wish, and it'll give rise to the familiar kind of branching diagram that we're shown all the time in discussions of the many worlds of the many worlds interpretation. The process can be repeated as many times as we wish, and once enough statistics have been obtained, each Kirk, there'll be 2 to the n of them after n repetitions of the procedure, compiles a report and writes it down on a piece of paper. When that's done, we'll have 2 to the n Kirks, each bearing a piece of paper, and each of those pieces of paper will bear an inscription. And some of those inscriptions are going to say that hypothesis 1 is the best confirmed, and some will say that hypothesis 2 is the best confirmed, and some will say that hypothesis 3 is the best confirmed. And this, as it stands, doesn't sound particularly encouraging, but let's not give up just yet. There is, after all, a difference that one can point to at this stage of the game between the fortunes of these three different hypotheses. There is, in particular, a trivial combinatorial proof that the pieces of paper that favor hypothesis 3 are going to vastly outnumber the pieces of paper that favor either hypothesis 1 or hypothesis 2. And it seems very natural and it seems very reasonable to at least wonder whether this observation, that there are many more pieces of paper favoring hypothesis 3 than there are favoring hypothesis 1 or 2, it seems very reasonable to wonder whether this observation can somehow be parlayed into an argument that the outcome of this experimental procedure, considered maybe as a whole, is somehow confirmatory of hypothesis 3 and disconfirmatory of hypothesis 1 and hypothesis 2. But look, that just can't possibly be right, because the distribution of inscriptions over these 2 to the n pieces of paper is a feature, after all, of the physical configuration of the world. And the evolution of the physical configuration of the world, as we've just been saying, is utterly and completely insensitive to the difference between hypothesis 3 and hypothesis 2 and hypothesis 1. And every feature of the physical configuration of the world would therefore be exactly as it is, whether hypothesis 3 was true, or hypothesis 2 was true, or hypothesis 1 was true. Let's try again. Suppose that when the single Kirk first steps into the transporter, at the very beginning of the experiment that we were talking about above, he happens to be well disposed for whatever reasons. Maybe he believes in a principle of indifference or something like that. He happens to be well disposed towards hypothesis 3. And now let the experiment run its course. And we'll be left at the end with 2 to the n Kirks on the surface of the planet. The vast majority of them, call them the threeers, are reassured and content. Their experience over the course of the experiment has seemed to them to be confirmatory of hypothesis 3, and they're even more confident now than they were at the beginning. They're vastly more confident now than they were at the beginning that hypothesis 3 is in fact true. And they're kicking back and they're having beers and they're exchanging anecdotes and what have you. And then there are much smaller groups off to the side somewhere who are loudly protesting that their experience, to their surprise, has turned out to be confirmatory of hypothesis 1 or hypothesis 2. And suppose we walk up to one of these threeers and we say, congratulations on everything's having worked out so well. I see that you and your friends are very pleased, but tell me, what do you have to say about that guy over there who is insisting that his experience has been confirmatory of hypothesis 1? And the threer says, look, this is not in the least surprising, and this is not in the least unfamiliar, and this is not in the least at odds with my conviction that hypothesis 3 is correct. It's a feature of every stochastic theory. It's in the very nature of stochastic theories. It's the very essence of stochastic theories, after all, that they allow for the possibility of bad luck. All chancy theories, and not merely self-locating chances, have the feature that, notwithstanding the theories being perfectly true, and notwithstanding the fact that a certain experimenter has done absolutely everything right, she may nevertheless end up with results that are profoundly misleading. And that's what's happened, and that's all that's happened to that poor schmuck over there in the corner. And this turns out not to be correct. And it'll be worth taking a minute to say clearly why. The crucial thing about ordinary statistical bad luck, insofar as the theory of confirmation is concerned, is that it can be depended upon not to persist. Suppose, for example, that the true stochastic theory of the world happens to entail that the probability of an A turning into a B when somebody says abracadabra is, say, 0.7. And suppose that some finite number of separate and independent investigators undertake to confirm this theory. Each of them takes an A and says abracadabra and takes note of whether or not it turns into a B, and then repeats the same process with another A, and so on. Now, so long as the number of repetitions is relatively small, and so long as the number of independent investigators is sufficiently large, some of the investigators are likely to run into precisely the sort of bad luck that the threer was alluding to above. But note that for any finite number of independent investigators, and for any arbitrarily small numbers, gamma and epsilon, there will be some finite number delta, such that once the number of repetitions is greater than delta, the probability that even one of the investigators will have recorded a frequency of A's turning into B's when she says abracadabra is farther than gamma from 0.7 will be less than epsilon. Another long sentence, but of a kind everybody's familiar with, I take it. And this is absolutely crucial to the way the business of confirmation works. This is what's at the bottom of every argument, to the effect that investigators who are sufficiently relentless in their collection of evidence and who are sufficiently rational in the way they take that evidence into account are all eventually, ideally, going to converge with one another and on the truth. And this is what secures the objectivity of the scientific project. And all of this is as diametrically opposed as can be imagined to the way things work in cases of self-location. Consider again the Kirk experiment. And start things out, as we've been doing throughout this discussion, with as small a number of independent investigators as is mathematically possible. Start, that is, with a single Kirk who steps into a transporter. And two Kirks arrive on the surface of the planet, and each of them observes and repeats and so on. And note that no matter how many such repetitions take place, the probability of there being a Kirk who ends up being in the blue outfit every single time, and the probability of there being a Kirk who remembers ending up in the green outfit every single time, and the probability of there being a Kirk who remembers ending up in the green outfit exactly 68% of the time, and so on, all of those probabilities are exactly 1. And they never go away. And so the lack of consensus among them is nothing at all like ordinary statistical bad luck. And the business of dismissing the testimonies of these sorts of Kirks on the grounds that there aren't very many of them is just going to amount, of course, to begging the question. And so the impossibility of any, this is the circularity that Sean referred to in his talk. And so the impossibility of any consensus ever emerging from these Kirks is apparently of the very essence of the kind of question that they happen to have decided to look into. And this is what sets this question entirely apart from ordinary statistical chance. Let's try once more. The point of the experiment we've been talking about, if there is a point to this experiment, if there ever was a point to this experiment, can certainly not have been to find out how many Kirks we were going to end up with, or how they were going to be dressed, or what it is that ends up getting inscribed on their pieces of paper. The objective third-person physical picture here is, after all, completely deterministic, and so no experiments were ever going to be required in order to find out about any of that. What these experiments were supposed to shed light on was rather the question of which of these Kirks was likely to be me. and which of these outfits and which of these inscriptions was likely to be mine. And all that has emerged, and of course we should have seen from the beginning that all that could have emerged is that for some Kirks, my experience and therefore my inscription favors hypothesis 1, and for some Kirks, my experience and therefore my inscription favors hypothesis 2, and that for some Kirks, my experience and therefore my inscription favors hypothesis 3. And suppose that we're finally willing to accept that the business of somehow objectively adjudicating among these different claims is hopeless. Is there anything at all still left to try? Well, what if we were to try to bust all this wide open by dispensing with the requirement that the science of these probabilities even turns out to be objective? What if somebody says in particular that it should not have come as a surprise and that it should not be treated as a problem, that cases like that claims like these, claims that is about the self-locating probability in a certain particular physical situation having been measured to be this or that, and claims that some particular theory of the assignment of self-locating probabilities to some particular situation having been confirmed or disconfirmed by experiment, and claims to the effect that some particular theory of the assignment of self-locating probabilities is even true or false. What if, as I said, somebody says that it shouldn't come as a surprise and it shouldn't be treated as a problem if all these kinds of claims are themselves irreducibly indexical? On this way of thinking, we should not say, and the science of such probabilities should not aspire to say, that this or that theory of the assignment of self-locating probabilities is well confirmed by experiment, or that there are good reasons to believe it, or that it is true or false of the world. What we should say, and all that the science of such probabilities should aspire to say, is that the theory in question is well confirmed for me by experiment, and that there are good reasons for me to believe it, and that it is true or false of the world that is centered on myself, centered in the Lewisian sense. So let's see. The first thing to say, the obvious thing to say, and I think the important thing to say, is that if probabilities like these are supposed to play a central role in scientific explanations, if probabilities like these are supposed to play the role, for example, of quantum mechanical chances, then this way of thinking is going to radically diminish the traditional, objective, realistic aspirations of the scientific project. And the question is why in the world we would even want to fool around with crazy shit like this when there are sensible and workable and flat-footedly mechanical ways of solving the measurement problem on the table, the ones that have been mentioned, hidden variables theories like Bohm's, collapse theories like GRW, and so on, that make no such baroque and suspicious and exhausting demands on our philosophical imagination. This reminds me, David Bohm used to tell a story that went like this. Look, what if history had been different? What if Bohm's interpretation of quantum mechanics had been discovered before the Copenhagen interpretation, and it's widely accepted and people are working with it, and all of a sudden Bohr waltzes in and says, look, I've got this other interpretation of quantum mechanics. It pays much more respect to the mathematical symmetry between position and momentum, so on and so forth. The only drawback is there turns out to be no real objective external world. You have to interpret science in a radically instrumental way, so on and so forth. Bohm's thought was this would have been dismissed as preposterous if people had already been working with another alternative. One is tempted to say a similar thing about this sort of scenario, but there are certainly deep and interesting and difficult questions about whether there is a way of, whether there is a coherent way of thinking here at all. And it'd be interesting to know the answers to those questions. The only person I know of who's made a serious attempt at working something like this out is Isaac Wilhelm. I don't know if Isaac is here. Anyway, Isaac Wilhelm, who's about to get his PhD at Rutgers, has written a paper called Centering the Everett Interpretation, which tries to pursue an idea like this. I recommend it to all of you. As for myself, I'm content for the time being merely to have shoved all of you to the edge of this particular precipice. And I guess I'll stop there.
Thanks so much, David. All right, so before we move on to a general discussion, our schedule has 30 minutes for a conversation between our two speakers, Sean and David. Like I said before, if you get tired of talking to each other before the 30 minutes is out, that's fine. We'll move on to general discussion whenever you're ready. So Sean and David, if you would like to unmute.
I'm unmuted.
I'm unmuted also.
I didn't have any particular agenda or list of questions. I just figured, Sean, you might have questions for David or the other way around.
So yeah, I mean, there's a lot of things to say. Let me just try to focus it as much as possible to be productive, right? Other than various rhetorical flourishes, I'm not that far away from a lot of what David says in his talk. But where I come down at the end of the day is, there is a certain way the world could have been had it been fundamentally stochastic, right? Like if something like GRW had been correct. I don't buy the part I disagree with most substantively about what David just said is at the end where he worries about the unlucky experimentalists in an Everettian universe and seems to insinuate that we don't have that problem in more conventional single world theories. I think we do have exactly that problem if you're in a cosmology that is infinitely big. There will be a large number of observers who are very, very unlucky one way or the other. So that problem doesn't go away. But aside from that, but that's not the main thing. I think that there is a certain way things could have been if that fundamental single world but stochastic ontology had been right. And Everett is fundamentally different from that. And I think that a lot of the resistance to understanding probability in Everett, the way that those of us who are pro-Everettians understand it, comes from a nostalgia for that kind of way the world could have been and sort of insisting that it must be like that or it doesn't make sense. So what I think is missing from David's account is if Everett were true and there were these self-locating uncertainties, what would you do? How would you deal with them? It's not optional. You can't say, well, I'm sad because it's not, the same thing that I thought I had when I thought it was just a truly stochastic frequency. The argument I tried to make was you have to deal with them in some way. There is an obvious way to deal with them, and it's very empirically successful. And I'm sure that David disagrees, but why don't I give him a chance to say that explicitly?
I mean, let's see. There's lots of ways that the world could have been, okay, that that are successful as skeptical scenarios, okay, in the sense that if somebody says, how do you know the world isn't like this? Okay, how do you know that everything wasn't created 5 seconds ago along with your memories and so on and so forth? And you have to say, yeah, I can't imagine how to prove that that's not the case. Okay, but what we would say about worlds like that is that these are ways the world could have been, which are hostile to the scientific enterprise. Okay, these are ways the world could have been in which it turns out that the inhabitants of that world are never able to come into possession of good reasons for believing that the world is like that, okay? That's, it seems to me, a handy way to distinguish between something that succeeds as a skeptical scenario and something that is a sort of viable candidate for a scientific theory of the world, okay? What you need to do in order to succeed as a skeptical scenario is to have a scenario such that you can come up and throw it in a guy's face and say, prove to me that it's wrong, and the guy is unable to prove that it's wrong, okay? What you need to be a substantive scientific theory, a sort of interesting candidate for a scientific theory of the world, is more than that. You need something that's empirically adequate in the way successful skeptical scenarios are empirically adequate, but it also has to include the possibility of a successful scientific enterprise, okay? That is, the world described by this theory, among the things that the theory has to entail is that it could be the case that inhabitants of the kind of world that the theory describes could come into a position of having good reasons to believe that that's the way the world is, okay? So, you know, and the way you do that, the way that's typically done is by noting the explanatory success of these theories and stuff like that. What's puzzling me, so you say, suppose we lived in a world like this. We'd have to do, I mean, I don't know what we'd have to do, you know, suppose we lived in a world like this, you know, there are these, there always are these scenarios where you say, that is, here's a temptation. You say, somebody tells you the marble is in one of these 5 boxes. I'm not going to tell you anything about which box it's in. What are you willing to bet that it's in box number 3? Okay. And it seems like the reasonable answer at first is to say, how the fuck should I know how much to bet that it's in box number 3? I have no clue which box it's in. Which part of I have no clue do you not understand? Okay. I have no clue. And then they'll say, but what if the guy is holding a gun to your head? Okay. And forcing you to bet? It's not clear to me why I should have more of a clue in that case than I had before the guy took out the gun. I haven't been told anything more about the marble. It seems to me what I should be saying when the guy takes out the gun is, this is really, really unfair, okay? Because I have no clue where the marble is, and your taking out the gun doesn't help me have a clue about where the marble is. I have no clue. A second related question. So I guess I don't understand this talk of we have to do something. I don't understand why it wouldn't be right to say in this kind of Everettian case, I have no idea. And somebody says, but how are you going to live? And the guy says, I don't know how I'm going to live. I have no idea where the marble is. That's the only honest thing for me to say. Okay. Another related question. Look, and here's something, and this is sincerely a question for the whole audience, I guess. I'm sorry, so maybe I shouldn't. All right, I'll give it. I'll just put it out there. There are lots of people who talk about, in such and such circumstances, these are the uniquely rational credences to have, okay? And in the same breath they say, but I'm separating here credences from things like chances or probabilities or anything like that. I don't believe in probabilities in this case. All I'm saying is that in this circumstance, these are the uniquely rational credences to have. I guess I'm puzzled by this kind of talk because I don't know, our aspirations for our credences, I take it, are nothing over and above tracking the chances that things are true. If I'm talking to somebody and the guy says, Mike, I'm almost sure the Yankees are going to win this year, okay? My credence is really, really high that the Yankees are going to win this year. And I say to the guy, so you think the Yankees' chances are good? Guy says, did I say anything about chances? I didn't say anything about chances. I said, I'm sorry, don't get upset. You know, you think that it's likely that the Yankees are going to win. Guy says, did I use the word likelihood? I didn't. I mean, this sounds like a part of a mafia movie where a guy's about to get beaten to within an inch of his life, okay? Because the guy's trying to be difficult. I don't understand what it means to say, I am almost certain that the Yankees are going to win, but I have no opinions whatever about the objective chance that they're going to win, or about the objective probability that they're going to win, or anything like that. I don't understand how these are going to be so separated from one another, particularly if we want these credences to do explanatory work for us. They have to be much more than that, okay? And if you say, look, this is, you know, this is what I expect to happen, or this is what I don't expect to happen, you have to ask them why you expect this to happen. The comparison you made with confirmation of fundamental physical theories is interesting here, okay? Certainly, we don't think there are objective chances that this physical theory is true or that that physical theory is true. But that's precisely why the only kind of criteria of rationality that we believe in connection with confirmation has to do with how to update our beliefs based on new evidence rather than what beliefs to have, okay? If anybody says the uniquely rational credence that you ought to have that string theory is true is 0.75, okay? The right thing to say is that's crazy. There aren't uniquely rational credences. The way probability theory, the way confirmation theory works is that people start off with all kinds of different prior probabilities, and all that can be rationally required of them is that they update them, you know, in accordance with Bayesian conditionalization or something like that. And they're updating them in that way precisely because what they aspire to in the way that they confirm or disconfirm theories is to get them in a position where their credences at the end of the day are just tracking the objective chances. So I'm sorry, this was a long-winded way of saying I'm puzzled by the distinction a lot of people make in these discussions by saying, hey, I'm not saying there are any probabilities here. I'm not saying there are any chances here. I'm just saying this is what your credences ought to be if you're rational.
So yeah, I mean, there's a lot going on there. I want to let other people have an option.
Yeah, I think that's a good idea too.
And probably many of the things I would say in response, one can conjure up what they would be. But let me briefly nod toward them just to be clear. You know, I don't, you be unsurprised to hear, I'm not sympathetic to the comparison of Everettian quantum mechanics with skeptical scenarios of last Thursdayism. For one thing, I think that Everettian quantum mechanics is very falsifiable, right? I mean, there are experiments going on to see spontaneous collapses of the wave function, which in my mind would falsify Everettian quantum mechanics. So I think it's a different bag in some way. The question of the credences versus chances, yeah, I mean, this deserves a lot more discussion, but again, if you think that the world, if you ask yourself, what would you do in a world that was Everettian? So in some real sense, there are no chances in the old-fashioned sense of something truly stochastic. What do you do? Well, I think what you do is, I don't mind if you use words like chances and likelihoods and so forth. I just say that, but what you mean is I'm putting credences on things. I mean, if the world were deterministic and you did have an opinion about whether the Yankees would win or not, I mean, obviously that's not a chance in the frequentist sense. It can only be a credence. There is some fact of the matter about whether the Yankees will win or not. You just don't know it. It's your
I guess I mean, maybe it's worth saying here I think I disagree with what you just said. Okay, it seems to me, given the sort of macro condition of the world now, okay, and this is what I was saying about the statistical postulate in the first part of my talk. I think there is a fundamental physical chance that the Yankees will win the World Series. It's also true that given the microstate of the world now, okay, the probability is either 0 or 1 that the Yankees will win the World Series. But I think that in order to make sense of statistical mechanics, and this was the thrust of the first part of my talk, in order to think that statistical mechanics is explanatory of thermodynamics and so on and so forth, you need also to believe, okay, that there is a fundamental chancy law, okay, of the form. Given a large ensemble of systems in this macro state, here's how many of them will be in this micro state, okay? This is a robust physical regularity of our world, okay? This is a real chance, okay? That is, the attitude towards statistical mechanics that the chances there are merely epistemic, I don't think is right, okay? If you believe that, okay, you know, it's a fact about the world, okay? You take 1 million ice cubes or something like that in identical macro states, okay? And then you make a list of how many of them are in this region, you know, or how many of the macro states, how many of the micro states fall in this subregion of the macro state, and how many of the microstates fall in that subregion, and ... Okay? You're going to get regularities there, okay? You may think one or two things. You may think those regularities obtaining follow a priori from the fact that I didn't know what the microstate was, okay? Response, how the fuck could that be true? Okay, what does the world care about whether or not you knew? Second option, this fact about the frequencies of microstates given a macrostate is an additional empirical law of nature, okay? The world could have been such that it obeys Newtonian mechanics, the laws of motion, but doesn't obey this other law, okay? If the world were like that, thermodynamics wouldn't be true, even though Newtonian mechanics would be true, okay? This is an addition. So no, I think there are real chances there.
Yeah, so I think I don't buy the distinction. I think that I would say almost exactly the opposite. I think that if you believe the whole package of macro states and micro states, the chances that we talk about in statistical mechanics can be thought of precisely as self-locating uncertainties in the set of all microstates that we could have imagined is compatible with that initial macro state. But let me end with sort of the more sympathetic version of how I think about this stuff. I do think that this kind of worry is the right one to have. You know, I think that if I were to stop being an Everettian for some principled reason, other than it was disconfirmed by experiment, which is always possible,
right?
The attitude that I'm most sympathetic to is simply metaphysical conservatism. The idea that what you're asked to buy in Everettian quantum mechanics is so much different than what we're sort of used to and what we're happy with and what we're familiar with, that one should naturally, as a methodological principle, be cautious and be wary about jumping into that. And that is, for me personally, it is more than balanced by the fact that as in the attempt to try to make sense of the laws of physics and how the world works, Everettian quantum mechanics is such a better fit to that than any of the alternatives that we have. So the argument that you give, you know, about, well, if we had Bohmian mechanics, et cetera, when as a working theoretical physicist who's trying to understand quantum gravity, I compare Bohmian mechanics or spontaneous collapse theories to Everett, it is an utterly unfair fight in my mind. So that's why I come down the way I do. You know, Everett is so much better at physics that I bite the bullet of saying, yes, we should be metaphysically radical in that sense. But I get it if people don't want to take that leap.
Sean, could I just ask one final question about that, I guess, before we open it up? I mean, of course, that's up to Jacob. Um, um, so, something like Everett, if it ends up being intelligible, and GRW are, of course, physically different claims about the world that could be distinguished from one another. But I'm puzzled about what it could mean to say Everett is so much better for doing physics than something like Bohm. The business of doing physics in either of them is exactly the same. It's solving the Schrodinger equation. I mean, in what sense could it be the case that for a workaday physicist, Everett is so much better for doing physics than something like Bohm?
Because as an Everettian, if someone says, here's the Hamiltonian, what happens? You answer it. As a Bohmian, someone says, here's the Hamiltonian, you have to say, but wait, what are these other ontological pieces you haven't told me about? What are the other variables in addition to the wave function? If you're doing quantum gravity, I think that's going to be a tall mountain to climb.
Good. Thank you.
All right, so I think we're done with the conversation between our speakers. We have a few extra minutes. I'm wondering if maybe we should take a 5-minute break before we commence with the rest of the discussion.
Yeah, that's a good idea.
Yeah, so let's take 5 minutes. We'll reconvene. My clock says 2:47 right now, so let's reconvene at 2:52, and then I'll just open the floor until 4 o'clock. So everyone take about 5 minutes.
Thank you, Jacob.